This room is an anechoic room. That is, it is free from acoustic reflections. And that fact makes this room very special from an acoustic point of view. This room is a reverberation room with walls, floors and roof treated to reflect as much of the acoustic incident energy as possible. And that makes, of course, the sound field in this room very, very special. And in particular, if you compare with anechoic. So the difference between these two extremes of rooms we will discuss in the upcoming presentation. The main difference between the two rooms you saw in the two video clips in the beginning of this is that the anechoic room, there you have no reflected sound waves. That means that the sound wave that reaches the observer is the direct sound wave radiated from the source. So no reflections whatsoever. Whereas in the second room, in the reverberation room, you have a very, very high number of reflected waves. And these reflected waves builds up standing waves, a large number of standing waves that cause these reverberating sound effects. In order to be able to calculate and analyze standing waves, one needs to be able to treat reflection and transmission of waves. And that is what we are going to deal with in the continuation of this presentation. So suppose now that we have two mediums here, medium 1 and medium 2, and that we have a plane, infinitely large plane interface between these two mediums. And also assume that the interface is located in the YZ plane. And we have an incident plane, incident sound wave here with a propagation angle theta I relative to the x-axis here. And then we have also a plane reflected wave with and a plane transmitted wave, or refracted wave, as it's sometimes called. So what we are going to do now is to discuss how to determine the propagation angles of the reflected and transmitted waves, and also the amplitudes of the reflected and transmitted waves, if we know from beforehand the angle of incidence, theta I, and the incident waves amplitude, and also the density and sound speed in both media, medium 1 and medium 2. So how can we determine the reflection and transmission angles? So let's start with that. Theta R and theta T. And also the amplitudes. But let's start with the angles. So the condition, it's the condition at the surface, at an infinitely small distance to the left of the surface and to the right of the surface. That is what we are going to focus on. Because on the incidence side, we have a certain wave pattern in the surface here. And from physical reasons, the pattern on the medium 2 side must be identical to the pattern at the medium 1 side. So it must be continuity in the pattern. So in order to continue this, if we project, if you see here we have the incoming wave, and these dashed lines here indicates 0,
as you can see here, 0 positions on the incoming wave. So in between here, we have maxima and minima in the wave pattern. And the same goes for the medium 2 side, the transmission side. So the dashed lines here is also 0 points, and in between we have minima and maxima. And if we want a continuity in the patterns here, then of course the distance here between the wavelength projected on the interface here must be equal, both on the medium 1 side and on the medium 2 side. So here is a wavelength on medium 1 side. So if you project that to the interface, you get this distance here. And here is a wavelength on the transmission side. And if you project that on the interface, you get this, which must be the same distance as for the medium 1 side. And as you can see here, the incidence angle and transmission angle are involved here. So from this condition, this boundary condition, you can formulate this rule, this boundary condition. So the incident wavelength over the sine of the incidence angle must be equal to the wavelength and sine of the angles for the reflected and transmitted waves. So, but let's go now to the reflection angle. If we assume linear sound propagation, which we do, then we know that the reflected wavelength must be equal to the incident wavelength, because we cannot get the frequency change caused by the reflection. So that's a consequence, from this linear system frequency conservation law. So that means that the reflection angle must be equal to the incidence angle. So, but how do we then calculate the transmission angle? Well, then we can use this law here, this coupling between the wavelength and angles, and reformulate. So if we use now, this simple relation between the wavelength and frequency and speed of sound, we can replace the wavelength with the ratio of the speed of sound and frequency. So this holds for the incidence wavelength, C1 over F, and for the transmission wavelength, we have C2 over F. And then we can remove the frequency, and then we get the relationship with only the known and unknown properties. So C2 and C1 here, remember that these two properties are known. And theta I is also known. So from this relationship, we can calculate the transmission angle, theta t. This is also known as Snell's law, that you may remember from fundamental school physics or optics. So if you consider this relationship now, if C2 is larger than C1, that is, if the speed of sound is higher in medium 2 than in medium 1, then you see here that this ratio here is larger than 1. So that means that for angles theta I that is large enough, then this right-hand side of this equation will be larger than 1. And then sine theta, this equation has no real valued solutions. So that means that we have a critical angle for which the right-hand side here is equal to 1. And that is the maximum allowed angle of incidence for the existence of plane waves on the transmission side. And that is denoted with the critical angle. So a plane transmitted wave only exists for incidence angles lower than the critical value. If C2 is smaller than C1, then there exists a transmitted plane wave for all possible incidence angles. We will actually come back to this in a later presentation. What happens? What is the field if we have angles of incidence higher than the critical angle? So now we have determined the angles, the reflected angle and the transmitted angle. So then we come to the wave amplitudes, the reflected and transmitted wave amplitudes, and that is a bit more complicated. So you have to stay focused now in order to follow. You can see this is a good example on how you use the basic equations and the complex quantities to calculate different field properties in an acoustic field. So how do you do this? Well, we have two unknowns now, the reflected wave amplitude and the transmitted wave amplitude. So we actually need two conditions to be able to determine these two unknowns. And the first condition is that, exactly like before, we need a continuity in the particle velocity in the along the interface here. So if we focus now on the normal direction, the normal component of the particle velocity, we can state the condition that the particle velocity on the incoming side, the incidence side, must be equal to the particle velocity on the transmission side. So, and we should evaluate this very, very close to the YZ plane, mathematically speaking, when x is equal to 0 for both these cases. So that is continuity in particle velocity, its normal component. The second condition is that we must have force balance. So if we cut out a volume element here over the interface surface, then the pressure acting on this surface must balance the pressure acting on this surface. So this force balance we can express as a continuity in sound pressure. So the sound pressure from the incidence side must balance or be equal to the sound pressure on the transmission side. So that is the two conditions we should use. So let's start now with this, and let us now assume, as usual, a single frequency incident wave. And let us express the incident complex, incident sound pressure as a complex quantity. So we replace, the time dependence, cos or sine omega t, with its complex exponential. And then it turns out here that for a given direction, then, we have a wave number components, kx and ky, that expresses sort of the wave pattern in the x and y directions. So these are so-called wave number vector components in x and y directions in medium 1. So if you go here, if we consider this blue arrow here as the wave number, so the y component here is the k1y, and the x component here is the x component of this vector. And the same goes then for on the transmission side. and for the reflected wave, of course. So in medium 1, we can also express the reflected complex sound pressure in the same manner then. The only difference here is, of course, the amplitude. And then, as you can see here, the sign of the wave before the wave number in the x direction. And that is caused by the fact that, see, the incidence wave is in positive x direction, whereas the reflected wave goes in the negative x direction. So that is the reason for the different signs here. Otherwise, since it's the same medium, then the angle of incidence is equal to the angle of reflection, then the magnitudes of this k1x and so this k1x must be the same in both cases. It's only the sign that is different. So that is the reflected complex sound pressure. Now, on the transmission side, then we have, you see here, the same sign as in the incident wave, minus plus, minus plus. The only difference here is, apart from the amplitude, of course, that we have index 2 here. And that indicates then that we have a different sound speed in medium 2. So the wave number is different. In medium 1, the wave number the magnitude of the wave number must be equal to omega over C1, whereas in medium 2, it must be equal to omega over C2. And that is reflected then in this notation K2 here. So this is now the complex sound pressures for all three components that we have in this problem. So let's go now for the boundary condition stating that the total sound pressure level in medium 1 must be let's go. Well, the total sound pressure field then in medium 1 is equal to the sum, because we can, since we have a linear system, then we can use superposition, and that means that we can sum the incidence and the reflected fields. So this is the total sound pressure field on the incidence side of the interface. And boundary condition 2 now, saying, if you remember that the sound pressure evaluated at the incidence side of the interface immediately at the interface side for x equal to 0 must be equal to the sound pressure in the neighborhood of the interface on the transmission side. That can be stated in this manner. So this sum, the incidence and the reflected waves, must be equal to the transmitted wave, evaluated then at x equals 0 at the interface position. So if we insert this and cancel out the common factors, we arrive at this expression. So the unknowns now, well, not unknowns maybe, but what we have to deal further with is this K1y and K2y. What are these? This first boundary condition, where the particle velocities immediately in front of and immediately behind the interface should be equal. That we can express with the equation of motion. You remember this equation of motion. So if we take the partial x derivative of the sound pressure fields, and if we time integrate to remove this time derivative here, then we can find the particle velocities. So we end up then with this expression for the particle velocity. The minus and pluses here depends on the direction, the x direction of the waves. You remember the reflected wave had opposite sign compared to the incidence and transmitted waves. So the choice of sign here, plus or minus, depends on which direction we focus on. Now we can introduce this wave number vector. In the general format of this wave number vector is like this, that you have three components, an x component, y component, and a z component. In our case, we consider this problem in, where kz actually is 0. So we only focus on the first two terms of this wave number vector. So we only have this kx and ky components. So if we have now, in general terms here, we have this wave number vector here, and the magnitude of this wave number vector, the length of the vector, must be equal to omega 2 pi times the frequency over the speed of sound c. And the components now of this, you have the x component kx, y component ky, and z component. So if we start with projecting this, the projection of the wave number vector in the xy plane, then we have this theta angle, the incidence angle, and the transmission angle in our cases. Here. Then we see that we can express this kx and ky components in terms of theta and this phi angle, because this projected component here is actually equal to k times sine of phi. So we find then this expression for the components of the wave number vector. This is the x component, this is the y component, and this is the z component. And in our case, since we have waves that propagates in the xy plane, this phi is pi half, or 90 degrees. So cosine pi half is 0, so this is cancelled out, and sinus phi here then is 1. So we have the components omega over c, cos theta, and sine theta. And that is what we are going to use in the boundary conditions now. So here we have them. The x components, we have this omega over c, plus or minus, depending on if it's positive or negative. And ky, sine theta, and minus always, since all of them is propagated in the negative y direction. So for the transmitted wave, we have this. Well, the incidence and reflected wave, we have this. Here we have the theta I, and for the transmitted wave, we have this combination here. So if we introduce these now in the boundary conditions, the first one for particle velocities, we find these three components then. The incident wave with cosine I, the reflected with minus, since we have a propagation in the opposite x direction, and for the transmitted with cos theta t here. And also the rho and c, of course, change when we pass the interface from 1 to 2. So this condition now, here, with these inserted and x equal to 0 now will give us this condition. So now we have this thing here, K1i and K2i. What are those? Well, according to Snell's law, we know that the incidence and transmitted angles must satisfy this condition. So this one, the second one here, is simply the inversion of these two times 2 pi in order to replace the frequency here with the angular frequency omega. And that means that this equation here is actually the same as saying that the y components of the wave number vector in medium 1 must be equal to the y component of the wave number vector in medium 2. So this is in fact the boundary condition that we used in order to determine this, to derive this Snell's law before. So this means now that this term here, this factor here, is identical to this factor, and we can simply cancel them out from the equation. So now we have one equation, well, the second equation actually. We already have one for the pressures, sound pressure amplitudes. So now we have two. So this is the force balance, the continuity in sound pressure. And the second one was the one we just derived for the particle velocity continuity. So these are now two equations with two unknowns. And the two unknowns are the reflected wave amplitude and the transmitted wave amplitude. So this is a linear system of equations that we can solve quite easily. And the solutions turns out to be possible to express in this way. So the reflected wave amplitude is equal to a factor consisting of rho and c for the two media and the incidence angle and transmission angle times the incident wave amplitude. And in the similar way, we can express the transmitted wave amplitude. So now we can introduce something that is called, reflection and transmission coefficients. So the reflection coefficient is defined as the ratio of the reflected wave amplitude over the incidence wave amplitude. And from the first equation here, you can see that this is the reflection coefficient. And in a similar way, you can introduce a transmission coefficient as the ratio of the transmission sound pressure amplitude over the incidence sound pressure amplitude and get this result. So this is important now to remember. So these are the reflection and transmission coefficients with respect to sound pressure. You can also introduce reflection and transmission coefficients with respect to particle velocity, but then these are defined as the reflected sound particle velocity over the amplitude of the incident particle velocity. And then these expressions will change. So remember now, these reflection and transmission coefficients are with respect to sound pressure. Okay, to summarize what we have derived here is, first of all, the two relations to determine the reflection angle and the transmission angle. So the second one for the transmission angle This one is actually this that you know from basic school, fundamental school, Snell's law. And then we have this reflection and transmission coefficients with respect to sound pressure that you can use to calculate the amplitudes, the unknown amplitudes of the reflected and transmitted waves. So this is basically what you need to be able to calculate many types of standing wave problems. And that's all for now.